So I'm going to talk about compound risk, and I'm going to talk about it as a tail risk problem. And I think that's pretty consistent with the way most people think about doing their stress testing. They think what we need to do is come up with a scenario which is plausible but extreme. Hard to know exactly how to translate that into probabilities, but that is kind of the idea. It has to be unusual, but not impossible. And I'm going to try to take that idea and build it into the compound risk framework. So a risk is some kind of a bad event, which is in the future, which could happen. And when we talk about risks, how do we describe them? We describe how bad it is and how likely it is. And once you know those two things, you can decide whether it's worth taking this risk or not, because the investor may well decide that this is not so damaging and he wants to go ahead and take the project anyway. And so, you know, there is a risk-return trade-off involved, but in order to do the risk-return trade-off, you've got to measure the risk as part of it. So compound risk, of course, says we might be able to do this one at a time, but if we're doing more than one at a time, how do we adapt what we know how to do to that problem? And I'm going to, first of all, use as an example something simple that we don't think of as a compound risk, but could. That is, we have stocks and bonds in our portfolio, and we could think about stress testing the stock part of our portfolio and stress testing the bond part of our portfolio as being two risks. We don't actually do that, but let's just think of how it would work if you did that sort of thing. Well, let's take, for example, the stress for stocks might be a 40% decline over the next 6 months. Stress for bonds might be a 10% drop over the next 6 months. These are actually both pretty extreme, but plausible. And in fact, if you look at a histogram of 6-month returns, you'll see that they're both at about the 1% quantile of that distribution. So what happens to this portfolio? Well, if you have the stock risk, you lose 24% of the value. If you have the bond risk, you lose 4% of the portfolio. And the risk manager has to figure out what to do next, because this is not really an answer. You don't know what the probability of one or the other of them happening is going to be. What you'd really like to do is come up with some way of combining these results to give you an overall measure of risk. And clearly this requires you deciding, you know, how similar are these two risks? Are they likely to both occur, or just one, or just the other, and so forth. So that's what we're going to try to do. And here are some examples to think about, which are a subset of the examples that, of course, we all are worried about. But I'm going to talk specifically about two risks, which are climate risk and market risk, which we can do with the tools in VLAB, because we have a way of doing stress tests for climate and a way of doing stress tests for market risk, but we don't know quite how to do the compound risk, and that's what we're going to talk about here. But we could also think about things like physical risk and transition risk in the climate space, or market risk and liquidity risk in portfolio management, market risk and risk. That is, that the risk is going to go up, is a risk. Inflation and unemployment, which Tobias was just talking about, climate and pandemic, macro risk, credit risk, and interest rate risk, and of course, everything, everywhere, and all at once fits right into the theme. So we need to know how dependent these risks are, and I'm going to try to formulate that question in a just some notation so we'll get used to it. So let's think about there being two risks, X and Y. We could think of them as being stocks and bonds, or we can think of it as being market risk and climate risk. And if U is some small probability, we can talk about the quantiles of these distributions. So we can find a quantile for X and a quantile for Y, which give you the same probability of being exceeded. And since we're going to use low values of U, we're going to get negative values for both these quantiles because we're talking about how much these two factors are likely to go down. And then we're going to be interested in the probability that one is in the tail given that the other one is, the conditional probability. And it turns out, of course, if you ask what's the probability that Y is less than its quantile, conditional on X being less than its quantile, that is exactly the same as the converse. So it's symmetric like in correlations. And we'll call this function lambda of U, where U is the quantile that the probability we're talking about. So in the statistics literature, there is actually a long tradition of looking at tails in this kind of way. And it's the original measure of tail dependence, which was published in the 60s, is the limit of this function as U goes to 0. And so we might call that the coefficient of tail dependence, or I'll tend to call it just tail dependence. And so what are the values we might expect to see of lambda bar? Well, I mean, there are a couple of things to say maybe before I answer that. You can see that we can define quantiles by using the data, or we can define quantiles just using ranks. And so that means that this tail properties are a function only of the ranks of the observations. And that means we don't really need the whole distribution. All we need is what's called a copula, which is the distribution of the ranks themselves. This is a simplification of the problem. In fact, we don't even really need the whole copula. All we need is the extreme part of the copula. And so when we talk about estimation, these are all possible ways of estimating the copula or tail dependence. So there's some situations where X and Y can't both be extreme at the same time. Might be in this interest rate example, we're concerned about bond prices falling or bond prices going up. Obviously, they can't both happen, but they're both extremes. In which case, the conditional probabilities are 0 for well, any U in that case, but maybe for extreme U's. So lambda is 0, and its limit is, of course, going to be 0. Another case that we think about all the time is that these two risks are independent. And if they're independent, then the probability of one doesn't depend on what the other one is. So this lambda function is just U by itself, and the limit when U goes to 0 is also 0. So the disjoint and independent and tail independent cases really have the same tail properties. Another is that they might be perfectly dependent. In other words, once you have X in this tail, then Y is always going to be in the tail. And that is also a polar case that we're interested in which case lambda of U is equal to 1. The probability of X being in the tail, given that Y is 1, and so the limit is 1. So we can go from 0 to 1 in terms of tail events which are uncorrelated, and tail events which are actually perfectly correlated. In practice, we're going to be interested in where we are on that spectrum between 0 and 1, but how do we adjust our formula for doing risk management? So I think the problem is the first line there. You'd like to find QX and QY such that the probability that X is not extreme and at the same time Y is not extreme, and that probability is something like 99%, 1 minus alpha. Okay, so you pick an alpha. This is your confidence that these things aren't going to happen. And if these things don't happen, then we have a lower bound on how much we could lose. And the lower bound I'm calling the stress loss here. And this is assuming that the valuation changes with X and Y in a nice little linear fashion, just like a factor model we have here. So the change in value might be firm value, it might be a portfolio value, it might be a bank's value. And that's the example we're going to look at, is this depends on the value of X and Y and the beta of X and the Y. And so the stress loss is just when X is equal to its lower bound, Y is equal to its lower bound. Okay, so we want to be 99% sure that any losses are greater, are not as bad as that number. Okay, so how do we do that? Well, there is a solution here which says we pick the quantiles with some value U star, then the relationship between U star and alpha depends on the joint probability of both of these being there. And that joint probability we can express as the conditional probability times the marginal probability, or in other words, approximately it's lambda bar times U. You can substitute in, and you can see that alpha is equal to 2 minus lambda bar times U star. Or in other words, U star is alpha divided by 2 minus lambda bar. So if we choose alpha, this tells us how we ought to pick our quantiles. If we've already chosen the quantiles, this tells us what the alpha is that we got from it. It doesn't really matter. So the only thing we need to know to adjust this is what we're going to use for lambda bar. I'm not going to give you the proof of this, sorry. So this is the little formula we're going to use. Once we have lambda bar, we can figure out which quantile we want for both X and Y. And these two cases that we've talked about, if lambda bar is 0, then we use alpha over 2. So this is the independence case. If lambda bar is equal to 1, then we use just alpha, because they're really the same event. Okay, so, and if it's somewhere in between, that's the formula for it. Possibly you're interested in, suppose we have 3 or 4 or more. I mean, this is kind of the formula you get for 3, as long as the probability that 3 events occur is negligible compared to the rest of this. Okay, there's a proof in here, but I'm going to skip it. I'm going to apply this to the stock and bond example. It turns out I'm going to show you some estimates which suggest that stocks and bonds have a lambda bar equal to 0, that they don't both have extreme down moves at the same time. That's not actually shocking. That's kind of what we would believe in for a lot of reasons, in which case the 60-40 portfolio should be evaluated not at, if I want an alpha of 1%, I'm not going to use 1%, I'm going to use U star instead. And U star is half alpha, so it's 0.5%. And when you look at the quantile for 0.5%, you get 11% for bonds, 48% for stocks. You plug it in, you get an estimate of the stress loss, which says for the 60-40 portfolio, the worst thing that might happen with probability, 99%, you would argue, would be that it would go down by 33%. Okay, so that's the logic. And so you can use these stresses with any portfolio. You can do a 70-30, you can do a 100-0, whatever. It just you plug in those betas. So how did actually the 60-40 portfolio turn out? Well, it turns out it did fall by 33% during the financial crisis, but the 1% quantile is less than that, which satisfies this inequality. I have a second example, which I think I won't do in any detail, but it's between US equities and international equities. And the reason for being interested in this is that stocks and bonds tend to not have extremes at the same time, and US equities and international equities tend to have a high degree of tail dependence. They're similar to each other. So when I calculate the stress losses here, I'm using a lambda bar, which is pretty close to 1. So I'm not going to do the example, but I think you see it. So this leads us to the question, how do we actually figure out what lambda bar is? And there is a large literature in statistics on how to do this. There's a survey by Fram, Junker, and Schmidt in 2005 that basically compares a bunch of them with Monte Carlo experiments and has sort of 4 classes of solutions. One is if you know the whole joint distribution of X and Y, you can, up to some parameters, you can use all your data and estimate those parameters by maximum likelihood, and then calculate from those parameters what the tail dependence looks like. But of course, if you don't know how to get the distribution right, you don't get the answer right. You could assume that you know the copula of this, which is less restrictive as an assumption, and then estimate the parameters of the copula using the ranked data, just the ranks. You could also assume, but that of course still assumes that you know the whole copula, and it's using observations that are far from extreme to tell you something about the extremes, and it's always a little perilous. You can look at threshold versions of the copula. So it's only a copula once you get past some threshold, and that makes some sense, but then you have to pick a threshold. And the fourth thing, which is what I'm going to do, is a non-parametric estimator, which is basically an empirical version of the copula. And it's totally simple and what comes naturally, but you sacrifice some precision by not making assumptions about more of the distribution. You're only using the tail information, and tails are, by their nature, not very well populated. So on the left is the bond stock tail function, and this on the right is the international versus domestic. And on the left-hand side, we have probabilities going to 0. We're looking at quantiles. This is each point here is 10 basis points. So this is 1%, 2%, up to 10%. And as you get further and further here, the question is, if you extrapolated it to 0, of course you have no data, but what we're doing is calculating empirically for any quantile. You calculate the quantiles of Y and X, and then you count how many of Y's are in this tail at the same time as X. And so it's a simple calculation, but there isn't much data when you get down here. So basically what you see is it's falling, but among other things, you see the numbers are actually, even at the top, are less than 10%. So lambda bar, I think, is fairly naturally thought of as being close to zero for stocks and bonds. For US and foreign stocks, you can see this is rising. And it might be rising all the way to 1, but at least here it looks like you might want to pick a number like 0.7 or something like that as an approximation to what the tail dependence really looks like. All these numbers can be thought about from a theoretical point of view as well. And obviously, if you're going to do this, you're going to be thinking pretty hard about how you think, how dependent you think these two factors are. And maybe that gives you some good insight. You can also do some Monte Carlo. Here's a simple example where Z is common to both X and Y, and Z is a student T. So if the student T is very fat-tailed, so it's only got 3 degrees of freedom, you get a picture more or less like the international and domestic stock. If you use 3 with 10 degrees of freedom, you get something that looks much more like the stock bond example. And if it actually were normal, then the limit is 0. It's a theoretical result, regardless of the correlations. Okay, so now I want to turn to what I think of as close as I come to a real example. I mean, you know, you're shortly going to see much more real examples than this, because Renee and Till have some beautiful examples of how to think about these problems. But this is sort of real. And when central banks are trying to figure out whether the financial system is fragile with respect to climate shocks, the question is, do they also have to think about market shocks? In other words, whenever you have a climate risk, are you going to have market risk at the same time? And what I mean by market risk is a drop in the aggregate stock portfolio. What I mean by climate risk is, in this case, it's a transition risk measure, which has to do with, energy and high emitting companies having stock returns which drop dramatically. So there are reasons that I've sort of casually written down here why you might expect them both to happen. And if we were able to do that, we might be able to come up with theoretical answers to whether we expect these to come together or to be uncorrelated, but I'm going to show you just empirically what's happening. I think I've already said all this. I should say that Dick Hayoun and I have a paper which develops these climate stress tests, does a lot of analysis of them, and tries to document whether they actually are giving realistic numbers. And we have now implemented these measures in VLAB, so I can actually just plug them in, and we have the capability to do compound stress tests. But what should I use for the numbers? That's where this talk is coming from. So if you look at, let's see. So if you look at the 6-month returns on the S&P, the 1% quantile, these are all log returns, by the way, so there's continuously compounded returns. The 1% quantile is 33% down. If you do the same thing for the stranded asset portfolio, which is our climate portfolio, it's 64% down. So it's more volatile. It's it's a sector bet, so it's not surprising that it's more volatile. And if you look at what we've estimated for each of these banks around the world, we have betas on these two factors, which are changing over time. Citibank beta for climate risk is in March of 2020, which is the beginning of the pandemic, was 0.66, and for market risk it was 1.53. So the separate damages are either 42% for climate or 50% for market risk at this point in time. So if you look at the measures of tail dependence, which is what we need to do to decide what quantile we should really use, we see a picture that doesn't look like any of the ones we've had before. And so the question is, do you extrapolate this one and then you say it's 1, or do you extrapolate down here and say it's 0? And I don't really know what the right answer is. It turns out that when you get to the 2% quantile here, the only events where both of these happen at the same time are during the financial crisis. And if I think about it some more, I'll probably understand why that makes it go down. But it's an observation anyway. And you would normally expect that kind of would be a few isolated instances, but not just one. Anyway, I'm not clear how I want to pick my lambda bar from this picture. And so I'm going to proceed with an arbitrary choice, which is, I think I'm picking 0.7 here, which is some compromise between those two answers. And if I do pick, let's see the rest. Let's see, wait a minute. Okay, well, I guess actually I misspoke. I think in the example I'm going to look at, I'm going to pick lambda bar is equal to 0, which says that these are independent events, in which case I need to use a quantile for 0.5% rather than a quantile for 1% in order to get a 99% confidence. And so if you do that, you end up with a stress loss of, well, it's 106%. That seems like a lot, but actually, since these are log returns, it's only 66% decline in terms of fractional declines. So if you look at the plots of the betas for Citibank, which we estimated dynamically so that using a dynamic conditional beta, so that the betas are basically the best forecast of what the beta is going to be in the next day using volatilities and correlations as you go. You see they've changed over time, but this time that I picked, which was March of 2020, is pretty much the peak of the market beta, but it's also a fairly high value of the climate beta. So I'd like to know, what was the stress loss at different points in time here? How has it changed over time for Citibank? And I can do that with VLAB by using quantiles that I calculate based on 0.5% quantiles. You plug them in, and this is a picture of what's the stress loss looks like. This is actually the positive of it, and you can see it was quite high here in March of 2020, which is where I did the calculation. But if you look today, well, if you looked in January anyway, it had dropped quite substantially, and then there was some increase because of with the banking turmoil, the market betas went up. Actually, the climate betas also went up at the end. So if we do this for the large banks, here are the market betas. Can't really see much there, except that they really went up during the financial crisis. And they also went up to some extent here in 2020. And you actually, some of them are quite substantial right at the end. And if you look at the climate betas, you see this really, the pandemic was a time where the climate betas were quite large, but they have really come back down since then. And zero here is kind of in the middle. It's not really clear. We're seeing much evidence today that the climate risk is a serious instability factor here. Calculating the stress losses, this is what you see. And this is what I suppose you might see if you were the regulator and you did the compound risk. If you do simple market risk, climate risk, it would probably be a different picture. You wouldn't have used any information from the market change. So this is kind of the outcome. There's a whole another piece of this research that I haven't done yet, which says, why are these betas changing? One answer to that is it's because of the holdings of the banks are changing. But one of the things you see is that they're very highly correlated. So it might be that they're all changing their holdings in the same way, but it might also be that there are other factors which make the betas go up and down, some of which might be the nonlinearities or accelerations due to enhancements due to the factors being large. That's obviously something that needs to be investigated. So I figured a good way to end this is just to say, well, this is the first stab. This is kind of an idea of how you might do this compound risk problem. It's a formulation of the problem, which works for this example. It might be harder to apply to some of the other examples, but there is a lot more research that can be done. We can use better univariate quantiles. We can use better measures of tail dependence. And we probably want to work on whether we need to change the impact equations from the nice linear factor model to something which has got some nonlinearities and other things going on. And or is there other information that would tell us what the betas are actually doing? So I'm going to stop here. Thank you. I'm not going anywhere, but
any questions for Rob?
Yes. Oh, Shahong. Okay. Why didn't I use your method? I'm going to talk to you about that.
So I find out, turns out, especially when you care about tail risk, you need to see the tail dependent corporate effect. That is the number of zero. Precisely in that case, many methods, especially this empirical calculus, this kind of thing, will underestimate the tail dependence.
Okay.
So I don't know what's not is a problem here.
Why? And that's just under. I mean, it's a bias or it's a.
Yeah.
Okay.
Severe bias.
I mean, it's certainly there's a lot of noise in doing this, but
it's not just noise. It's also it's bias.
Okay.
Kind of like some heterogeneity bias.
Question for future research.
Yes. Let me put it on my. Actually, it's already there. It's number one. Or number two, I guess, right? Yeah, anyway, but thank you. Yeah, right.
In the conference theme, say that when concurrent multiple shocks hit economies, firms, financial markets, and societies, the combined impact can be far greater than the sum of its parts. That's a depends on how these tail events accumulate.
Right.
If you add two random variables, if the scale of the sum is greater than the sum of the scales, you must be in the domain of attraction of a stable distribution with alpha less than 1. So it's even heavier tailed than Cauchy. Would you actually maintain that that's true? That the shocks are I mean,
Well-
they're not Gaussian, so they've got much heavier tails than alpha 2 is Gaussian, but alpha less than alpha equal 1 is really out there.
Yeah, no, I mean, I realize that using anything less than alpha 0.01 is way out there, but I'm not, so reading the description of this, it's talking that I interpret that as talking about whether the factor model is really linear or not, and whether shocks to one change the betas on the other or something like that, you know, whether or whether if the shock is twice as big, is the beta still the same beta, or is it beta is a function of X as opposed to, and so that doesn't affect the distribution of the X and the Y themselves. So I mean, I'm not thinking about I don't think that sentence is about feedback from the impact to the factors. Could be, but at least I didn't think of it that way. But stable distributions are on the table here. Could definitely be here.
And for 2 more.
Yeah, Frank, hi.
You know, one thing that struck me is some notion of distributional regime switching across expansions and contractions.
Right.
You might think about that. There's a literature, as you know, right, that started off asking the question, you know, why don't stocks and bonds move together?
Yeah,
So it's very much linked to your stock and bond example.
right.
And it came around to a different answer. The answer was, you know, well, they do move together, but they are possibly correlated in expansions and negatively in recessions. So if you smear it all together, it looks like they're unrelated. So, I mean, you may or may not believe that particular.
Yeah, you're right.
But the basic idea in general of some regime switching associated with the business cycle, you need to think about the business
Right.
cycle. And if you're looking ahead, you've got to wait for the recession.
Well, that's why I plotted those betas to see if your eye was going to pick up business cycle in the betas. And you know, this is exactly what I'm having in mind with this number 3. You know, this is a very useful slide here. I get I get the point to it. But you know, when we look at these things, when we look at the S risk and so forth, the betas are changing over time, and the betas go up during the financial crisis. Okay, why is that? Is that a regime shift, or is that just anyway? I agree. Interesting. Yes. Hi. Yeah, Victor.
Hi, Rob.
Hi.
How should we think about when these kind of extreme events do not quite align exactly together? They are maybe off a little bit. There's some lead-lag relationship that complicated the compounding.
So if I did it on a daily basis, you could have these causality from one to the other, and it wouldn't look like tail dependence because they wouldn't be extreme at the same time. By using this sort of a 6-month return, I think most of the cross correlations would be already happening, but in the climate case, maybe not. So I think there is a question, how do you do compound risk if the timing is different? You know, one happens before the other one, and maybe it's there's a causal relationship. Do you have time after the first one hits to build up your balance sheet for the second one? I'm not sure. I mean, I think you still might have to think about it as a joint event, even though one part of it happens before the other one. The unemployment that we are sort of worried about now is something we could have predicted would be following inflation. And I think a lot of people did. I mean, I think a lot of the risk managers probably saw those as two outcomes, which might be sequential, but you've got both of them. Is that?
Yeah, the sequential problem, and when you are putting it exactly right, when one kind of like before you even recover from one, there's some remaining lag of it. That's another one count.
Right.
So,
Okay, we can talk more.
Yeah.
Thank you. We done?
Right.
Thank you.
All right, we're on for a short break. We're a little behind schedule, so we'll meet again at 10:35.